Hi, in this video we're going to take a look at rational numbers. Now, rational numbers are simply fractions of integer numbers. So things like, for example, 1/2, minus 22/7, and so on. These are all fractions of integers that can be positive or negative, and those are called rational numbers. Examples of irrational numbers might be things like square root of 2. That's an irrational number. Pi is also an irrational number. So any real number with a finite number of digits is also a rational number. So for example, 0.45 can simply be written as 45 divided by 100, so that is a rational number. Similarly, if we take a look at this long one here, 0.123456789, which has 9 digits after the decimal point, then that is actually also a rational number. We can just write it as 123456789 divided by 10 to the 9. In that same vein, 8.3/4 is also rational because the top number is a rational number, the bottom number is also rational, and a fraction of two rational numbers is also a rational number. How do we get that? Well, 8.3 is the same thing as 83 divided by 10, and divided by 4, and if we work out the multiplication, we simply get 83/40. So 8.3/4 is the same thing as 83/40, so that is a rational number. 8.3 divided by 1.4, same thing there. We can write that essentially, if we multiply by 10 above and below the fraction, then we have 83/14, or you can also work it out this way. So that is also a rational number. So any real number that has a finite number of digits after the decimal point and a finite number of digits before the decimal point is a rational number. So let's take a look at the fraction class. That is used in Python to represent rational numbers, and that comes from the fractions module. There is a fraction class in the fractions module that we can use to handle those numbers. So the first thing we'll need to do in our code is to import the fraction. Either we can import the entire module, or we can just simply import what we need from the module. So we'll import the fraction class. And then we can use the constructors of the fraction class to construct new fractions, new rational numbers. So for example, x equals fraction of 3, 4, that will be 3/4, 3 divided by 4. We have fraction of 22/7, right? That will be 22/7. And fraction 6, 10 will give us 6/10, which is 3/5. So fractions are automatically reduced by the fraction class. So in that example, when we take fraction of 6/10, that will actually give us fraction 3, 5, 3/5. It will do that automatically for us. It will find the, it will basically reduce or simplify the fraction as far as it can. Negative signs, well, yes, rational numbers can be negative, and when you look at a fraction, you can really put your negative sign either above or below the line. It doesn't matter. And because it doesn't matter, Python chooses to always put the negative sign with the numerator. So if you were to write fraction 1, -4, you'll end up with a fraction -1, 4. It will switch the negative sign to the numerator. But it means the same thing. They're both the same number. So let's look at the constructors in a little bit more detail. We've seen the first one, where we have to specify the numerator and the denominator. If we don't specify the numerator, it will default to 0. If we don't specify the denominator, it will default to 1. We can also create a fraction from another fraction object. We can also create a fraction from a float, and we'll take a look at that in a minute, as well as decimal. And decimals and floats are both representations of real numbers. So basically we can take a real number and cast it or convert it to a fraction using these two variants of the fractions constructors. And an interesting one too is we can pass in a string. Now we've seen that before with integers, right? We can pass a string that evaluates to an integer, and we can create an int out of it. So very similar here. We can pass in a number, let's say 10, right? So that's really going to be an integer, and we can create a fraction where we're creating an integer in the numerator, right? And then the denominator is going to be 1 because it's not specified. So when we get that, it's actually equivalent to fraction 10, 1. So we can pass in things like that. We can even pass in a real number, 0.125. This is a float. 0.125 is 1/8. And in fact, when we do that, we get fraction of 1,8. What's more interesting is that you can actually specify your fraction in this format here using a slash. So the string 22/7, which is 22/7, will actually get created as a fraction 22,7. So that's really handy to have that around. Now the standard arithmetic operators are supported, plus, minus, as well as other mathematical operators too. But these standard arithmetic operators result in fraction objects as well. If you add two fractions, you get another fraction, all right? Two rational numbers, you get another rational number. If you subtract, multiply, or divide rational numbers, you end up with rational numbers as well. So for example, 2/3 times a half, well, that's 2/6, which is 1/3. And so if we write fraction 2, 3 times fraction 1, 2, we'll get fraction 1, 3. So again, Python will do the multiplication for us and also automatically reduce, right? So it will go from 2/6 to 1/3. Similarly, we have that with addition. Python will find the greatest common denominator, which in this case is 6. So 2/3 plus 1/2 ends up as 7/6. And in fact, that's what we will get as well in Python. Now we can also recover the numerator and the denominator of the fraction objects by using the numerator and denominator properties of our fraction object. So for example, let's say we have fraction 22,7, then x.numerator will return 22, it will be an integer, and x.denominator will also be an integer, and in this case it will return 7. Now, let's get back to this statement that we had earlier that floats have a finite precision. Now, we'll examine floats in a lot more detail in an upcoming video, but for now, we have a computer, and any number that we can store in the computer is finite. So, floating point numbers are also finite in the sense that you can only use so many digits to represent any particular number. So, in any computing language, floats have a finite precision. We don't have an infinite amount of numbers that we can use. So what that means, remember what we said, that any real number that has a finite number of digits is a rational number. Well, that means that in Python, and in any programming language for that matter, any float object actually can be written as a fraction. They are actual rational numbers. We don't think of them that way, but they are rational because they have a finite number of digits that represent them. So if we look at fraction 0.75, again, that's a float with a finite number of digits. This is 3/4, and we'll end up with fraction 3,4. If we look at fraction 1.375, well, that is actually 11/8. So let's take a look at something interesting. We're going to work with irrational numbers, numbers that are not rational, that we know are not rational, like pi and square root of 2. And let's see what happens. So we'll import math first so we can grab pi. So x will be fraction of math.pi. And when we look at the result of that, this is what we get. So pi is an irrational number, but Python was able to find an approximation using a rational number. Same thing with square root of 2. If we take y equal to fraction of math.square root of 2, then we get this big fraction here. Now, pi and root 2 are both irrational numbers. But of course, what happened is that internally they're represented as floats, right? Math.pi is a floating point number, but it is a finite precision. So, because they're finite precision, they're expressible as rational numbers. But they are just an approximation. So pi is not equal to this fraction here. Square root of 2 is not equal to that fraction there. They're approximately equal to that. So now one word of warning, because I've shown you some kind of very clean examples with 1/8 and 3/4 and so on. But there's a really important caveat, and we'll look at that in a lot more detail again when we cover floats in an upcoming video. But for right now, because we're talking about these rational numbers, I want you to be really aware of one problem that we have. If we look at 1/8, now 1/8, which is 0.125, has an exact float representation. It is 0.125, and it can be represented as a float exactly in Python. So we get, fraction point of 0.125 is fraction 1,8. We've converted that float to this fraction here of 1/8. But 3/10, which is 0.3, so 0.3 as a float, actually does not have an exact representation. And what happens when we then try and convert that to a fraction is that we get this big, horrible fraction here. We don't get fraction 3,10 as we might expect. And that's because 0.3 isn't exactly 0.3 when it's stored as a float. It's slightly different. How different? Well, let's take a look. If we print 0.3 up to 5 decimal points, or up to 5 digits after the decimal point, this is what we get. Hey, that looks good. That's 0.3. So 0.3, 0.3, 0, 0, 0, 0, that looks good. Well, let's expand the number of digits that we use. And this is what we get. So if we go to 25 digits after the decimal point, this is the number that's actually being stored, not 0.3. Now that would not be the case with 1/8. With 0.125, it would be 0.125 and then all zeros after that. And we'll get to why when we cover floats. So that's really important to remember, and that's why that we got that huge fraction. Now we can do something that constrains the denominator when we're converting a float, let's say, to a fraction. So given a fraction object, so we can create a fraction object, remember, from either using integers or using floats, and we can then find an approximate equivalent fraction where the denominator is constrained. So what do I mean by that? Well, and by the way, we'll use this limit denominator instance method where we can specify the max denominator. So what this does, it finds the closest rational number, which could be equal, but the closest one. It'll find the closest rational number to this fraction, but the denominator will be constrained so that it will not exceed max denominator. So let's take a look at an example. If we look x equals fraction of math.pi, which remember was this big horrendous fraction here, which evaluates as a float to this number here, which is an approximation of pi. We can choose to take this fraction and tell Python, well, give me the closest fraction where the denominator is no greater than 10. So how close can we get with a denominator no greater than 10 to this number here? To, pi basically. And we will get 22/7. And if we actually look at the float equivalent of that, well, this is 3.1428. So you can see we're correct up to the second digit after the decimal point. Now, similarly, we can tell Python to find the closest fraction, the closest rational number, where the denominator does not exceed 100. And it will calculate and find that 311/99 is the closest we can get. And if we evaluate that as a float, this is what we get, 3.141414 recurring. So you can see we're a little bit more accurate, a little closer to the actual value of pi than 22/7. Now we can push that up even further. Let's say we go with a denominator no greater than 500. Then this, 355/113, is a closer approximation of pi, with the constraint that the denominator be no greater than 500. If we evaluate that, we get 3.141592, and this is where, we get the, we match all the digits up to this 92 over here. Okay, and you can keep bumping up that limit. So let's take a look at some code and see how all that works.